15 years without a single change. Then suddenly, now, Earth's official alien contact policy is rewritten. One rule stands out: no contact without United Nations approval, and it drops just weeks before the expected close approach of the interstellar visitor 3I-ATLAS. The timing is impossible to ignore. The tone, almost rehearsed. Was this planned? Or are we witnessing quiet panic behind the scenes of science? Because updates like this just don't happen by accident. Stay with me, because by the end of this video you'll see why the question isn't if we're preparing for contact, it's who has already made it happen. If the 3I-ATLAS mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The No Reply Clause and 3I-ATLAS. Why this is explosive. Picture this. You're scrolling through a scientific paper on a Tuesday afternoon, and buried in the middle of page 7, you find a single sentence that changes everything. Pending the outcome of appropriate international consultations, no reply shall be sent to a confirmed extraterrestrial intelligence. That's it. 20 words. No fanfare, no press conference. Just a quiet rule dropped into the revised SETI Post-Detection Protocols draft published on Archive in late 2025. By the way, that's the official search for Extraterrestrial Intelligence Institute. Now, you might think this is bureaucratic housekeeping, the kind of thing scientists update every decade or so to keep their paperwork tidy. You would be wrong. Because here's where it gets interesting. That draft was released right around the same time astronomers announced the discovery of 3I-ATLAS, the third confirmed interstellar object ever detected entering our solar system. Not from the Kuiper Belt, not from the Oort cloud, from somewhere else entirely. The object was spotted on July 1st, 2025 by the ATLAS survey telescope in Chile, moving at velocities that confirm it originated outside our star system. Its perihelion, the closest approach to our Sun, is scheduled for late October 2025. As of this recording, 3I-ATLAS is already inside the orbit of Mars, approaching us at speeds that make conventional solar system objects look like they're standing still. So let me ask you this. Why would a rule explicitly forbidding anyone from sending a direct reply to extraterrestrial intelligence suddenly appear in an official document right before an interstellar visitor arrives in our neighbourhood? Is that timing remarkable, or is it just coincidence? Hold that question. Let's back up and explain what reply to extraterrestrial intelligence actually means in practical terms. We're not talking about philosophical debates or think tank workshops. We're talking about physically transmitting a message, a radio beacon, a laser pulse, anything that could be interpreted as intentional communication from Earth. Under the old protocols, the ones that have been in place since around 2010 or earlier, there was guidance suggesting consultation and coordination, but nothing explicitly forbidding an individual or organisation from making contact. The language was softer. Words like should and may left room for interpretation. But this new draft? It uses the word shall. That's legal language. That's a command, not a suggestion. Now here's the thing. The previous major revision of these protocols hadn't occurred in over a decade. This isn't routine. The International Academy of Astronautics, the body responsible for maintaining these guidelines, doesn't update them on a whim. They convene committees, hold conferences, solicit feedback from the global scientific community. The fact that this revision landed now in 2025 with this specific clause about replies, and at the same time as 3I-ATLAS is making headlines, creates what you might call a perfect storm of timing. New protocol, interstellar object, global attention, speculation everywhere. 3I-ATLAS is not just any space rock. It's the third interstellar object we've ever confirmed, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. But unlike those previous visitors, 3I-ATLAS is arriving during a period of unprecedented observational capability. We have the James Webb Space Telescope now. We have Hubble still operational. We have ground-based observatories with polarimetric and spectroscopic instruments that can dissect the object's composition in ways we couldn't 5 years ago. And what they're finding is, well, we'll get to that. But suffice it to say, the data is unusual enough that people are paying very close attention. So here's the scenario. Imagine you're part of a private SETI research group. You've been scanning the skies for years, hoping to catch a signal, a techno-signature, anything that suggests we're not alone. And then one day, you detect something. Maybe it's a radio pulse from the direction of 3I-ATLAS. Maybe it's an optical flash. Maybe it's something in the infrared spectrum that doesn't match any known natural phenomenon. Under the old rules, you might have the option to respond, to send a message back to say, "We see you, we're here." But under the new protocol, you don't have that option anymore. You're required to notify the appropriate authorities, archive your data, and wait. Wait for consultation. Wait for the United Nations to weigh in. Wait for diplomats and lawyers and ethicists to reach some kind of consensus about whether humanity should speak at all. Who gets to talk first? That's the question the protocol is answering. And the answer, as of now, is nobody. Not until we all agree, or at least until the people in charge agree. That's a fundamentally different posture than we've had before. Now let me be clear. Many people will tell you this is just policy housekeeping. They'll say the International Academy of Astronautics is simply modernising outdated guidelines to reflect current technology and geopolitical realities. They'll point out that the protocol has always emphasised international coordination, and they're not wrong. But the clause itself, the explicit prohibition on replies, the use of binding language, that's new. That redefines the entire framing of any future contact scenario. It shifts the question from should we respond to who decides if we respond and when. This rule isn't hidden in some classified document. It's public. It's posted on 3I-ATLAS, freely accessible to anyone with an internet connection. But how many people have actually read it? How many people understand what it means? And, more importantly, how many people realise that this rule is already on the books, waiting to be invoked the moment something triggers it? So here's where we're going. Over the next several parts, we're going to dig into what this revised protocol actually says, line by line. We're going to trace the timeline of how it was developed and when it was released. We're going to examine the oddities surrounding 3I-ATLAS, the interstellar object that seems to have arrived at exactly the right moment to make this protocol relevant. And we're going to look at how people are reacting, from mainstream scientists to conspiracy theorists broadcasting from their basements. Because if this rule is already in effect, and if something gets detected today, or tomorrow or next week as 3I-ATLAS makes its closest approach, then we need to understand who holds the microphone. Are we being primed to stay silent? Part 2. What the revised protocol actually says. The document is titled SETI Post-Detection Protocols Progress Towards a New Version, authored by Garrett and colleagues, published in 2025 on Archive. It's not short, it's not simple, but if you're going to understand what just changed, you need to know what's actually written in there. So let's break it down, piece by piece, and compare it to what came before. First, the scope has expanded dramatically. The old protocols, the ones from 2010 or earlier, focused almost exclusively on radio signals. That made sense at the time because radio was the primary medium for SETI searches. But the new draft acknowledges that technosignatures can take many forms: optical lasers, infrared waste heat from megastructures, anomalies in polarimetric data, even particle emissions that don't fit natural models. The definition of detection is no longer limited to a beep from the stars. It's anything that suggests the presence of technology, intentional or otherwise. Second, verification steps have been tightened. Under the old rules, if you detected something, you were encouraged to confirm it independently, but the process was somewhat informal. The new draft mandates multiple independent confirmations from different observatories before any public announcement can be made. It requires archiving of both raw and processed data in tamper-proof storage systems. It specifies that frequency bands used for detection must be protected from interference. These aren't suggestions, these are requirements. The goal is to prevent false alarms, to ensure that when something is announced, it's real. Third, data sharing and open access have been codified. Once a detection is verified, the data must be made available to the global scientific community. No hoarding, no proprietary claims. This is a direct response to concerns that arose after 1I/Oumuamua, when some data was initially restricted or delayed. The protocol wants to ensure transparency at least among scientists. Whether that transparency extends to the general public is another question. Fourth, and this is critical, the protocol establishes an International Academy of Astronautics post-detection subcommittee. This isn't just a group of astronomers, it's a multidisciplinary team: scientists, legal experts, ethicists, communication specialists. Their job is to coordinate the response, to advise on what should be said, to whom, and when. They become the central node in the decision-making process. If you're wondering who controls the story, start here. And then there's the clause, the one that started all of this. No reply shall be sent to a confirmed extraterrestrial intelligence pending the outcome of appropriate international consultations. Let's compare that to the older language. The 2010 version, if it addressed replies at all, used phrases like should consult or may consider. The shift from should to shall is enormous. Should is advice, shall is mandate. The new protocol makes it clear no single organisation, government or individual is authorised to reply on behalf of humanity without broad consultation. That consultation, by implication, would involve the United Nations, specifically the Committee on the Peaceful Uses of Outer Space. Now here's a critical detail that often gets overlooked. The protocol is advisory. It's not a binding international treaty. It doesn't have the force of law, at least not yet. The document itself describes it as a living document, meaning it's expected to evolve as circumstances change. But here's the thing about advisory documents. They become binding through adoption. If enough governments and institutions treat the protocol as authoritative, it effectively becomes law, even without a formal treaty. And given that the International Academy of Astronautics has significant influence in space policy circles, that's a real possibility. Let me give you a scenario to illustrate what this means in practice. Imagine a private SETI group, maybe based in Silicon Valley or Finland, detects a clear, unambiguous signal. It's verified. It's real. Under the old rules, they might hold a press conference. They might even consider sending a reply. Something like, "We received your message. Here's ours." But under the new draft, that's no longer allowed. They have to notify the International Academy of Astronautics subcommittee. The subcommittee reviews the data, convenes meetings, consults with the United Nations. Weeks pass, maybe months. During that time, the group that made the detection is legally and ethically bound not to respond. They have to wait. And who knows what happens during that waiting period? Other nations might respond in secret. The signal might disappear. The moment might be lost. But the protocol goes further. It also addresses smaller details that might seem mundane but are actually quite significant. For example, it specifies that all detection data must be archived in formats that are resistant to tampering. It requires that frequency bands used for SETI be protected from terrestrial interference, which means coordinating with telecommunications regulators. It even discusses the need for protocols around public messaging, how to frame announcements, how to manage public expectations and prevent panic. These aren't just scientific guidelines, these are governance frameworks. They anticipate not just the science of detection, but the politics and psychology of what happens next. So when people say this is just a routine update, ask them this. Since when do routine updates completely redefine who has the authority to speak for the human species? Since when do they embed explicit prohibitions on communication into what used to be a set of best practices? This isn't cosmetic, this is structural. The reply/no reply question has been moved from the realm of philosophy into the realm of official policy. And that policy sits inside a full governance framework that determines not just what we say, but who decides what we say. Now, here's the uncomfortable part. The protocol assumes that detection will happen through official channels, through recognised institutions with established credibility. But what if it doesn't? What if detection happens through a crowdsourced project, through amateur astronomers, through someone outside the system? The protocol tries to account for that by requiring notification, but it can't enforce compliance. And that's where things get murky. Because if someone detects something and decides to respond anyway, what happens? Does the international community condemn them? Do governments intervene? Do we end up with competing messages going out into the cosmos, some authorised, some rogue? The protocol doesn't answer that. Maybe it can't. What it does do, though, is make one thing very clear. The era of individual or institutional autonomy in this domain is over. If you detect something, you no longer own that information. You no longer control the response. The protocol has collectivized the decision-making process. Whether you think that's wise or necessary or dangerous, depends on how much you trust the institutions being given that authority. But one way or another, the game has changed. Part 3. The Timeline Forensic. How long has this been coming? If you're suspicious about timing, you're not alone. When people hear new protocol drops and interstellar object arrives in the same breath, the natural question is, did they know? Was this rushed through because of 3I-ATLAS? Or is the overlap just coincidence? To answer that, we need to trace the timeline step by step and see where the pieces fall. Let's start at the beginning, the original Declaration of Principles Concerning Activities. Following the detection of extraterrestrial intelligence was drafted in 1989. It was the first formal attempt to establish guidelines for what humanity should do if we ever received a signal from another civilization. The declaration laid out basic principles: verify the detection, notify relevant authorities, make the discovery public, coordinate international responses. It was aspirational, more of a philosophical statement than a legal framework. But it was a start. In 1995, a supplemental protocol was added, specifically addressing the question of replies. That document acknowledged that responding to a signal was fundamentally different from detecting one, and it called for international consultation before any reply was sent. But again, the language was soft. It suggested consultation. It didn't mandate it. And there was no enforcement mechanism, no subcommittee, no formal process. It was guidance, not governance. Fast forward to 2010, and we get what's often called the streamlined version. This update consolidated previous documents, clarified some procedural steps, and brought the protocols in line with developments in radio astronomy and international space law. But even then, the focus was primarily on detection and notification. The reply question was still treated as secondary, something to be addressed if and when it became relevant. Then, in 2022, something changed. The International Academy of Astronautics SETI Committee began discussing a comprehensive revision. Meeting minutes from that year indicate that the committee felt the existing protocols were outdated, particularly given advances in detection technology and the increasing involvement of private actors in space exploration and SETI research. They wanted a protocol that could handle not just radio signals, but optical techno-signatures, infrared anomalies, maybe even physical artifacts like interstellar probes, and they wanted clearer guidance on the reply question, because that issue had become more contentious as more people started thinking seriously about active SETI. The revision process took time. Drafts were presented at the International Astronautical Congress in 2023 and 2024. Feedback was solicited from the global scientific community. Revisions were made, and then, in late September or early October 2025, the draft was posted publicly on ARXiv. That's the document we've been discussing. That's the one with the no-reply clause. Now here's where 3I-ATLAS enters the picture. The object was discovered on July 1st, 2025 by the ATLAS survey in Chile. Initial observations confirmed it was on a hyperbolic trajectory, meaning it came from interstellar space. By mid-July, astronomers had calculated its perihelion for late October, around the 30th. Media coverage began picking up in August as more data came in from Hubble, JWST, and ground-based observatories. By September, 3I-ATLAS was a headline, so the timeline looks like this. The protocol revision process started in 2022, well before anyone knew 3I-ATLAS existed. Drafts were circulating internally in 2023 and 2024. The object was discovered in July 2025. The protocol was posted publicly in late September or early October 2025, just as media coverage of the object was intensifying. Does that sequence suggest the protocol was rushed out in response to 3I-ATLAS? Not necessarily. The revision process follows a predictable pattern: committee meetings, conference presentations, public comment periods, final drafts. These things take years. You don't throw together a comprehensive governance framework in a few months, especially not one involving multiple international bodies. The timeline suggests that the protocol was already in the pipeline, and its publication just happened to coincide with the discovery and approach of the object. But here's the problem with that explanation. We don't know exactly when the no-reply clause was finalised. Was it part of the draft from 2023, or was it added later, maybe in 2024, or even early 2025? The public documents don't specify, and that gap leaves room for speculation. Because if the clause was added after 3I-ATLAS was discovered, then the timing starts to look less like coincidence and more like reaction. We don't have proof either way. We have a timeline that's suggestive but not conclusive. There's another angle to consider. Scientific processes are often opaque to outsiders. Committees meet behind closed doors, drafts circulate among a small group of experts before being released publicly. So even if the revision process started in 2022, it's possible that details, including the reply clause, were being debated and refined right up until the final publication. And if those debates were happening in mid-2025, right around the time 3I-ATLAS was making waves, then the decision to include that specific language might have been influenced by the object's arrival, even if the overall revision was planned years in advance. Here's what we can say with confidence. The protocol was not snapped together overnight. The revision process has a documented history stretching back at least 3 years. But the timing of its public release, just as an interstellar object is approaching our Sun and generating global attention, is undeniably striking. Whether that's coincidence, prudent planning, or something else, depends on how much you trust the institutions involved. And that brings us to the question nobody's asking out loud. If the protocol wasn't rushed out because of 3I-ATLAS, then why does it feel like it was? Maybe because the object itself is raising questions that the protocol seems designed to answer. Maybe because the arrival of an interstellar visitor, especially one that's behaving strangely, makes the idea of contact feel suddenly less hypothetical and more immediate. Or maybe because we're wired to see patterns to connect dots even when the connections aren't there. But here's the thing, even if the timing is coincidence, the protocol is still real, the clause is still there, and 3I-ATLAS is still coming. So whether the two are connected or not, we're about to find out what happens when governance meets the cosmos, and that's going to be interesting no matter how the timeline shakes out. Part 4. 3I-ATLAS, the object that sharpened the headlines. Let's talk about the visitor. 3I-ATLAS isn't just another piece of cosmic debris. It's the third confirmed interstellar object ever detected in our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. But unlike its predecessors, 3I-ATLAS is arriving during a golden age of observational astronomy. We have tools now that we didn't have even 5 years ago. And those tools are revealing things about this object that don't quite fit the script. The object was identified on July 1st, 2025 by the ATLAS survey, a network of telescopes designed to detect near-Earth objects and potential impact threats. The name ATLAS stands for Asteroid Terrestrial Impact Last Alert System, which gives you a sense of what these instruments are built for, spotting things that could hit us. But this time, they spotted something that couldn't possibly hit us, because it's not from around here. The trajectory was immediately recognised as hyperbolic, meaning the object is moving too fast to be gravitationally bound to the Sun. It came from somewhere else, and after it swings past us, it's heading back out into interstellar space. The orbital details are remarkable. Perihelion, the closest approach to the Sun, is calculated for around October 30th, 2025, at approximately 1.4 astronomical units. That's inside the orbit of Mars, close enough to get a good look, but not so close that it poses any risk to Earth. After perihelion, the object will continue outbound, making its closest approach to Earth sometime in December 2025. By then, it'll be moving away from us at speeds that make pursuit impossible with current technology. We get one shot to study this thing, and that shot is happening right now. So what are we seeing? That's where things get interesting. The James Webb Space Telescope has been trained on 3I-ATLAS since late July, and the data is, to put it mildly, unusual. Spectroscopic analysis reveals a coma dominated by carbon dioxide, with a carbon dioxide to water ratio of about 8:1, plus or minus 1. That's extraordinarily high. Most comets, even comets from our own solar system, show the opposite ratio. Water is usually the dominant volatile, with carbon dioxide playing a supporting role. But 3I-ATLAS flips that script. Why? We don't know. Maybe it formed in a different kind of molecular cloud, one with a different chemical composition than the one that spawned our solar system. Or maybe something else is going on. Then there's the polarimetry data. Observations from ground-based telescopes show a deep negative polarization branch, meaning the way light scatters off the object's surface or coma is unusual. The inversion angle, the point where polarization changes sign, is around 17 degrees. That's a signature astronomers haven't seen before in comets. It suggests the material composing the object, or the particles being ejected from it, have properties that don't match any known comet analogues. Again, this could be explained by exotic but natural chemistry, or it could be something else. And then there are the more speculative claims. Some reports, primarily from tabloid sources, have suggested that the object is emitting metallic compounds, specifically nickel alloys, at a rate of about 4 grams per second without detectable iron. If true, that would be extraordinary, because natural comets don't emit metals in that way. But these claims are unverified. They're based on preliminary spectroscopic data that hasn't been peer-reviewed or confirmed by independent observatories, so we have to treat them with caution. They're intriguing, but they're not evidence. Not yet. There's also the question of the object's behaviour. Early observations showed no long tail, which is unusual for a comet approaching the Sun. Comets typically develop tails as solar radiation heats their surfaces and releases volatiles. But 3I-ATLAS was initially quiet. Then, in late August, the Keck Observatory detected what's called an anti-tail, a feature that points toward the Sun rather than away from it. Anti-tails are rare but not unheard of. They occur when larger particles are ejected from the comet and lag behind in its orbit, creating an optical illusion. But combined with everything else, the anti-tail adds to the sense that this object is behaving in ways we don't fully understand. So here's the what-if question. Could these anomalies be explained by natural processes? Absolutely. Interstellar objects come from different star systems, different chemical environments. They might have compositions we've never seen before. The high carbon dioxide ratio could be a signature of formation in a colder, denser region of a molecular cloud. The polarimetry data could reflect unique dust grain properties. The metallic emissions, if they're real, might be a byproduct of some exotic surface chemistry we haven't encountered yet. Natural explanations exist for everything we're seeing. But what if they're not natural? What if 3I-ATLAS is something else? A probe, maybe. An artifact. A piece of technology sent from another civilization to explore other star systems, the way we've sent Voyager and Pioneer into interstellar space. If that's the case, then the timing of the protocol revision starts to make a lot more sense. Because if you knew, or even suspected, that an interstellar visitor might be artificial, you'd want rules in place about how to respond. You'd want a framework for decision-making. You'd want to make sure nobody did anything rash, like broadcasting a message without authorization. Now let me be clear. Most scientists who've looked at the data still favour natural explanations. The consensus, if there is one, is that 3I-ATLAS is a comet, albeit an unusual one. But consensus isn't proof, and the data we have so far is incomplete. We're still in the middle of the observation window. More data is coming in every day, and until we have a complete picture, we can't rule anything out definitively. But here's what we can say. 3I-ATLAS stands at the intersection of science and speculation. It's the kind of event that challenges our assumptions, pushes the boundaries of what we think we know, and forces us to ask uncomfortable questions. Whether it's natural or engineered, mundane or extraordinary, the object is already serving as a test case for the very protocols we've been discussing. Because if this is what the universe sends us when we're not looking, what happens when we're paying attention? And that question, more than any specific data point, is why 3I-ATLAS matters. It's why people are watching. It's why the protocol revision feels so timely. Because whether the object is a cosmic snowball or a piece of alien technology, its arrival raises exactly the kind of scenario the protocol is designed for. Detection, verification, consultation, response, or no response. The framework is in place. Now we just have to see if anyone follows it. Part 5. Immediate reactions, scientists, live streams, and the social feed. The story of 3I-ATLAS isn't just being told in scientific journals and press releases. It's being told on YouTube, on Twitter, on live streams hosted by people broadcasting from their living rooms. And the narratives being spun in those spaces are wildly different from the ones coming out of NASA and the European Space Agency. This is where the battle for public perception is happening, and it's messy. On one side, you have the official scientific voices. NASA's blog posts emphasise caution and ongoing study. Phrases like "no threat to Earth" and "still under analysis" dominate the messaging. The European Space Agency has published a FAQ addressing common misconceptions about the object. The tone is measured, reassuring, almost deliberately boring. The message is clear. This is interesting science, but not cause for alarm. It's a comet. It's weird. We're studying it. Move along. On the other side, you have the alternative media ecosystem. YouTube channels with names like Cosmic Secrets and Classified Truth are cranking out videos with titles like Alien Probe Confirmed and They're Hiding the Truth About 3I-ATLAS. These videos rack up hundreds of thousands of views. They splice together clips from official press conferences, overlay ominous music, and draw connections between the protocol revision and the object's arrival. The implication is always the same. The authorities know more than they're saying. This isn't just a comet, it's a cover-up. Let me give you an example. One popular livestream host responding to the protocol revision said this: "When there's nothing to hide, they release information naturally. But this document, this is a gag order. This is them telling us that if something happens, if we detect something, if someone sees something, they're not allowed to talk about it without permission. And that permission comes from the UN? Come on, you really think the UN is going to let you know if aliens show up?" The host went on to frame the no-reply clause as evidence of preemptive control, a way for governments to monopolise the narrative before anyone else has a chance to speak. And here's the thing, that argument resonates with a lot of people, because there's a kernel of truth in it. The protocol does centralise decision-making. It does require consultation before any response. And if you're someone who's already sceptical of institutions, who already believes that governments withhold information as a matter of course, then the protocol looks less like prudent governance and more like confirmation of your worst suspicions. Social media has amplified this divide. Memes circulate showing the protocol document next to images of 3I-ATLAS, with captions like, "They knew," or "Coincidence? I think not." Hashtags like alien probe and gag order trend alongside more measured discussions of cometary chemistry and orbital mechanics. The conversation fragments into echo chambers, each reinforcing its own narrative. Scientists talk to scientists, conspiracy theorists talk to conspiracy theorists, and the average person trying to figure out what's real gets caught in the middle. But here's what's fascinating. Both sides are using the same source material. They're both reading the protocol. They're both looking at the data from JWST and Hubble. They're both aware of the timeline, but they're arriving at completely different conclusions. Why? Because they're asking different questions. Scientists are asking, what does the data tell us about the object's composition and origin? Conspiracy theorists are asking, why are they telling us this now? And what aren't they telling us? The first question seeks information. The second seeks motive. And those are fundamentally different modes of inquiry. So where does that leave us? The protocol is now a talking point in a much larger cultural debate about trust, transparency, and authority. For scientists, the no-reply clause represents prudent restraint, a way to ensure that humanity doesn't do something reckless or uncoordinated in a moment of historic significance. For skeptics, it represents evidence of control, a mechanism for gatekeeping information and suppressing independent voices. Both interpretations are internally consistent, both are supported by selective readings of the same documents, and both are shaping public perception in ways that will matter if and when something extraordinary actually happens. The credibility question looms large here. Who do you trust? Do you trust NASA, with its decades of exploration and peer-reviewed science? Or do you trust the independent researcher broadcasting from their basement, free from institutional constraints? Do you believe the official explanations, or do you suspect they're sanitized versions of a more complicated truth? These aren't easy questions, and they don't have obvious answers, because institutions do sometimes withhold information, and independent voices do sometimes get things spectacularly wrong. What's undeniable is that the same protocol text is fueling two very different narratives. The science narrative, we're updating our procedures to reflect modern technology and international cooperation. The suspicion narrative, they're setting up a framework to control the story before it breaks. And both narratives are being amplified by the arrival of 3I-ATLAS, an object strange enough to serve as a blank screen onto which people can project their hopes or fears. Here's the uncomfortable truth. The battle for public perception is already underway, and it's not being fought with facts. It's being fought with framing. It's being fought with rhetoric and imagery and emotional appeals. And the outcome of that battle will determine how people react if something genuinely extraordinary is detected. Will they trust the official channels, or will they turn to alternative sources? Will they believe the science, Or will they believe the conspiracy? The protocol might govern who speaks on behalf of humanity, but it can't govern who people choose to listen to. And that might be the bigger problem. So as 3I-ATLAS approaches perihelion, as more data comes in, as the story continues to unfold, ask yourself this. What narrative are you choosing to believe, and why? Because the question isn't just what is 3I-ATLAS. The question is, who controls the story, and who controls the contact? And the answer to that question might tell us more about ourselves than it does about the object hurtling through space. Part 6. Techno-signature expansion. What we can and can't detect now. When most people think about CT, they picture a radio telescope pointed at the stars listening for a signal. That image isn't wrong exactly, it's just incomplete. Because the universe of things we can detect, the signatures that might indicate technology, has expanded far beyond radio waves, and the 2025 protocol update reflects that expansion in ways that fundamentally change what we're looking for and how we'd respond if we found it. Let's start with the basics. A technosignature is any observable phenomenon that suggests the presence of technology. Classic CT focused on narrowband radio signals because those don't occur naturally. If you detect a signal at precisely 1.420 MHz, the frequency of neutral hydrogen, and that signal is tightly focused and modulated in ways that suggest information content, you've probably found something artificial. Natural processes don't produce narrowband signals. They produce noise, broadband emissions that span a wide range of frequencies. So for decades, SETI was synonymous with radio astronomy. Listen for the beep. Hope it repeats. But technology has advanced, and so has our understanding of what might constitute a technosignature. The 2025 protocol explicitly acknowledges this by broadening the definition of detection to include optical and infrared laser pulses, megastructure anomalies like Dyson spheres or Dyson swarms, particle emissions that don't fit natural models, and even polarimetric signatures that might indicate artificial structures or materials. This isn't science fiction. These are things we can actually look for with current or near-future technology. Optical SETI, for example, searches for brief, intense flashes of laser light. If another civilization wanted to get our attention, they might send a pulsed laser signal strong enough to outshine their home star for a fraction of a second. Our telescopes can detect that. Projects like the Optical SETI program at Harvard have been scanning for these kinds of events for years. And while they haven't found anything definitive yet, the technology is mature. It works. If someone out there is flashing a laser at us, we could see it. Infrared searches look for waste heat. Every civilization that uses energy produces waste heat as a byproduct. If a civilization is advanced enough to harness a significant fraction of its star's energy, maybe by building a Dyson sphere or a swarm of solar collectors, that structure would glow in the infrared. The James Webb Space Telescope wasn't built to look for alien megastructures, but it could detect them if they exist. WISE, the Wide Field Infrared Survey Explorer, has already catalogued billions of infrared sources. Astronomers are combing through that data looking for anomalies, things that are too bright or too structured to be natural. Particle and ion sensors can detect charged emissions from objects passing through space. Comets emit ions as their surfaces sublimate under solar radiation. But what if an object emits particles in ways that don't match natural comets? What if the composition is wrong, or the rate is wrong, or the distribution is wrong? That's potentially detectable. And if the emissions include industrial compounds, things like refined metals or synthetic molecules, that's even more interesting. Polarimetry measures how light is scattered off surfaces or through clouds of particles. Different materials scatter light differently. Natural comets scatter light in predictable ways based on the size and composition of their dust grains. But if an object's polarization signature doesn't match any known comet analogue, that's a red flag. It doesn't prove artificiality, but it demands closer investigation, and that's exactly what we're seeing with 3I-ATLAS. The polarimetry data doesn't fit, it's anomalous, and while anomalous doesn't mean artificial, it does mean we need to look harder. But here's the challenge. Detection limits and false positives are everywhere. Natural processes can mimic technosignatures in surprising ways. Pulsars, for example, were initially mistaken for alien beacons when they were first discovered in 1967. The signals were so regular, so precisely timed, that astronomers briefly considered the possibility they were artificial. They even nicknamed the first one LGM-1 for Little Green Men. But further analysis revealed a natural explanation. Rapidly rotating neutron stars. No aliens required. The same problem exists across the spectrum. Stars surrounded by dusty debris disks can produce infrared signatures that might look like waste heat from a Dyson sphere. Comets can produce ion tails that contain unusual compounds if their chemistry is exotic. Optical flashes can be produced by asteroids tumbling in sunlight, reflecting light in ways that create brief bright spots. For every potential technosignature, there's at least one natural explanation we have to rule out first. This is why the protocol emphasizes cross-confirmation and independent verification. If you detect something strange in one wavelength, you need to check it in other wavelengths. If one observatory sees an anomaly, you need other observatories to confirm it. You need to archive the raw data so other scientists can analyze it independently. You need to rule out terrestrial interference, satellite glints, instrument artifacts, software bugs. The list of things that can produce false positives is long, and every single one has to be eliminated before you can credibly claim you found something extraordinary. Now, apply all of this to 3I-ATLAS. We have JWST data showing an unusual carbon dioxide to water ratio. We have polarimetry data showing a signature we've never seen before. We have unverified reports of metallic emissions. Each of these, taken individually, could have a natural explanation. Exotic chemistry, unusual dust grains, measurement errors, but taken together, they create a pattern of anomalies that's hard to ignore. And this is where the detection landscape gets complicated, because we're operating in a grey zone between definitely natural and possibly artificial. Most things we see in space are definitely natural. A tiny fraction might be possibly artificial, and distinguishing between those categories is extraordinarily difficult. The protocol tries to address this by mandating a multidisciplinary approach. Don't just ask astronomers, ask chemists, ask materials scientists, ask engineers who work with spacecraft and know what artificial objects look like. Ask statisticians who can evaluate whether a pattern is genuinely anomalous or just a product of noise and observer bias. Build a team that can look at the data from every conceivable angle before making any definitive claims. But here's the speculative angle that keeps people up at night. What if a technologically engineered object is designed to hide? What if it's meant to look natural at first glance? If you were sending a probe to another star system, would you want it to be immediately obvious that it's artificial? Or would you want it to blend in, to pass as a comet or asteroid until it gathered enough data or decided to reveal itself? We design our own spacecraft to minimize detectability sometimes. Stealth satellites exist. Reconnaissance probes exist. Why wouldn't another civilization do the same? If an object is deliberately mimicking natural signatures, our detection tools might not be good enough to spot it unless we look very, very carefully. And that's where the expanded technosignature framework becomes critical. Because if we're only looking for radio beeps, we might miss the laser pulses. If we're only looking at optical wavelengths, we might miss the infrared glow. If we're only measuring bulk composition, we might miss the subtle isotopic ratios that don't match any known natural process. The more ways we can look, the harder it becomes for something artificial to hide. So here's the tie back to the protocol. With broad technosignature definitions, the reply rule becomes far more relevant, because we might detect something that doesn't look like a classic alien beacon at all. It might look like a comet with weird chemistry. It might look like an infrared source with unusual spectral features. It might look like an object with polarization properties we can't explain. And at that point, the question becomes, do we treat it as natural until proven artificial, or do we treat it as potentially artificial and proceed with caution? The protocol assumes the latter. It assumes that any detection, in any wavelength, that can't be immediately explained by natural processes should be treated seriously and subjected to the full verification and consultation process. That's a conservative approach. It errs on the side of caution, but it also means that ambiguous detections like 3I-ATLAS with its suite of anomalies fall into the protocol's jurisdiction. They trigger the framework, they require the consultation, and they potentially trigger the no-reply clause, even if we're not 100% sure what we're dealing with. The expansion of detection tools increases our reach, but it also increases ambiguity. We can see more, we can measure more, but we can't always interpret what we're seeing with perfect clarity. And when the stakes are this high, when the question is, did we just detect evidence of extraterrestrial technology, ambiguity is dangerous. It's the space where speculation thrives, where narratives diverge, where trust breaks down. The protocol's job is to manage that ambiguity, to create a structured process for navigating uncertainty. Whether it succeeds depends on whether people trust the process, and that trust, as we've already seen, is far from universal. So the question is no longer, did we hear a beep? The question is, did we see or sense anything that might be artificial? And that's a much harder question to answer, because the universe is full of strange things, natural strange things, and telling the difference between natural strangeness and artificial strangeness might be the most important distinction humanity ever has to make. The tools exist, the framework exists. Now we just have to hope we're looking at the right things in the right ways at the right time, and that when we find something, we know what to do about it. Part 7. Legal and diplomatic exposure. How UN consultation could play out. Let's talk about what happens after detection. You've confirmed something. Multiple observatories have verified it. The data has been archived. The anomalies can't be explained by any known natural process. You're 95% confident you're looking at a techno-signature, maybe even direct evidence of extraterrestrial technology. Now what? This is where the protocol's legal and diplomatic machinery kicks in, and this is where things get complicated. The protocol says, no reply shall be sent pending appropriate international consultations. That phrase, appropriate international consultations, is doing a lot of work. It's vague enough to be flexible, specific enough to imply a process. So let's unpack what that process might actually look like, who's involved, and what could go wrong. First, the institutions. The International Academy of Astronautics is the scientific body that issued the protocol. They're not a government. They're not a treaty organisation. They're an independent academy of experts, recognised globally for their work in space science and policy. If a detection happens, the IAA would convene their post-detection subcommittee, the multidisciplinary team we talked about earlier. This subcommittee would review the data, assess the credibility of the detection, and make recommendations about next steps. But the IAA doesn't have enforcement power. They can't make nations do anything. They can't prevent a rogue actor from sending a message. What they can do is provide legitimacy. If the IAA subcommittee says, this detection is credible and warrants international consultation, that carries weight. Governments listen. Media outlets listen. The scientific community listens. The IAA becomes the authoritative voice in the conversation, at least initially. Next step, the United Nations, specifically the Committee on the Peaceful Uses of Outer Space, known as UNCOPUOS. This is the UN body responsible for international space law and policy. It's where treaties like the Outer Space Treaty of 1967 were negotiated. It's where issues like space debris, satellite collisions and planetary protection are discussed. And it's the logical venue for discussing how humanity should respond to a confirmed extraterrestrial detection. UNCOPUOS operates by consensus. That means every member state has to agree before any formal resolution or recommendation can be adopted. That's slow, that's cumbersome, and that's by design. The UN doesn't rush into things. But in this case, slowness might be a feature, not a bug. Because the decision to reply to an extraterrestrial intelligence, or not to reply, is arguably the most consequential decision humanity has ever faced. You don't want to make that call in a hurry. But here's where it gets tricky. What if consensus can't be reached? What if some nations want to reply and others don't? What if the debate drags on for months or years while the signal fades, or the object moves out of range? The protocol doesn't answer these questions. It assumes consultation will happen, but it doesn't specify what happens if consultation fails. There's also the International Telecommunication Union, the ITU, which regulates radio frequencies and telecommunications globally. If a reply involves broadcasting a radio signal, the ITU would need to be involved to ensure the transmission doesn't interfere with existing terrestrial communications or violate international frequency allocations. That adds another layer of coordination, another potential choke point. So let's map out the pathway. Detection happens, verification happens, the IAA subcommittee convenes, they review the data and recommend consultation. The recommendation goes to UNCOPUOS. UNCOPUOS debates. Member states weigh in, experts testify, committees form, reports are drafted, months pass. Eventually maybe a consensus emerges. Either we reply or we don't reply, or we defer the decision pending more information. If the decision is to reply, then someone has to draft the message. Who does that? A committee of linguists, scientists, philosophers, a single nation, the United Nations itself. And what does the message say? Do we introduce ourselves? Do we share information about our civilization? Do we ask questions? Do we say nothing substantive and just acknowledge receipt of the signal? These aren't trivial questions. Every word, every symbol carries potential implications, and once a message is sent, you can't take it back. But here's the scenario that worries a lot of people. What if a private citizen or organisation detects a signal and decides to respond without waiting for consultation? The protocol says they're obliged to notify authorities and refrain from replying, but it can't enforce that obligation. There's no SETI police force. There's no international law with teeth that can stop someone from pointing a transmitter at the sky and pressing send. Maybe a Silicon Valley billionaire decides humanity is moving too slowly and takes matters into their own hands. Maybe a government, acting in secret, decides to send a reply as part of a classified national security operation. Maybe a rogue scientist, frustrated with bureaucracy, decides to broadcast on their own. The protocol anticipates these scenarios, but it doesn't have mechanisms to prevent them, and that's a gap, a big one. There's also the question of secrecy versus transparency. The protocol emphasizes open data and public notification once detection is verified. But what if a detection is classified for national security reasons? What if a government decides that information about the signal or the object is too sensitive to release publicly? The protocol has no authority over national security classifications. If a state decides to keep something secret, they can, and that creates a two-tier system. Public science operating under the protocol's rules, and classified operations operating under no rules at all, or at least no rules we know about. Historical analogues are instructive here. The Outer Space Treaty of 1967 established principles for space exploration, including the idea that space is the province of all humankind, and that nations can't claim sovereignty over celestial bodies. That treaty has been remarkably successful, considering it's held for almost 60 years. But it succeeded because it addressed issues where consensus was relatively easy to achieve. Nobody was living on the moon in 1967. Nobody had immediate economic interests at stake. The treaty could afford to be aspirational, but a reply to extraterrestrial intelligence? That's different. The stakes are existential. The implications are unknowable, and consensus might be impossible. Some nations might see contact as an opportunity. Others might see it as a threat. Some might want to engage. Others might want to hide. And those disagreements aren't theoretical. They're cultural, political, rooted in different worldviews about humanity's place in the universe. So what does this mean for 3I-ATLAS? If the object's anomalies can't be explained naturally, if evidence mounts that it might be artificial, then the protocol kicks in. The detection is verified. The IA subcommittee convenes. Consultation begins. And at that point, the world is watching. Not just scientists, not just governments, everyone. Because the question of whether to respond or how to respond becomes a global referendum on who we are as a species. Do we speak with one voice, or many? Do we trust the institutions we've built, or do we bypass them? Do we proceed with caution, or do we leap into the unknown? The protocol tries to create a framework for answering those questions, but frameworks are only as strong as the trust that supports them. And if that trust breaks down, if people decide the process is rigged or the consultation is a sham, then the protocol becomes irrelevant. Someone will respond anyway. And we'll find out whether the universe cares about our internal politics. The phrase UN consultation sounds bureaucratic, mundane. But it's potentially the gatekeeper for who speaks, or doesn't, in our first encounter. It's the hinge point between science and global decision-making. And whether it holds depends on questions we can't answer yet. Questions about trust, about legitimacy, about whether humanity is capable of acting collectively when the stakes are this high. The framework exists. The process is defined. Now we just have to see if anyone follows it, or if someone decides they know better. Part 8. Defense, Signals Intelligence, and Dual-Use Fears. There's an uncomfortable overlap between space science and national security that most people don't think about. But if you're going to understand why the protocol matters, and why its timing might be more than coincidence, you need to understand that overlap. Because detecting techno-signatures isn't just a scientific endeavour, it's also, potentially, an intelligence and defence concern. And when those two worlds collide, things get murky fast. Let's start with history. Early radar astronomy was developed using military hardware. The same radar systems designed to track incoming missiles and enemy aircraft were repurposed to bounce signals off the Moon and nearby planets. The first radio telescopes were often dual-use facilities, serving both scientific and defence functions. Even today, some of the most powerful radio dishes in the world are operated by or in cooperation with defence departments. The line between civilian science and military intelligence has always been blurry in space research. Now apply that to SETI and technosignature detection. If you're searching for artificial signals from space, you're using tools and techniques that are fundamentally similar to signals intelligence. You're scanning frequencies. You're looking for patterns. You're trying to distinguish intentional transmissions from background noise. That's not just astronomy. That's SIGINT, and intelligence agencies care about SIGINT. A laser flash could be extraterrestrial communication, or it could be a directed energy weapons test from an adversary. A megastructure's infrared signature could be evidence of alien engineering, or it could be a classified military installation with unusual thermal properties. An anomalous particle emission from an interstellar object could be exotic natural chemistry, or it could be propulsion exhaust from a probe, ours or theirs, that someone doesn't want detected. The technologies we use to search for aliens are the same technologies we use to monitor each other, and that creates dual-use problems that the protocol doesn't fully address. Here's a scenario. A private SETI group detects something. They follow the protocol. They notify the IAA. The IAA reviews the data and confirms it's anomalous. But before the IA can make a public announcement, a government steps in. National security classification. The data is sealed. The detection is removed from the public domain. The researchers are told to keep quiet. Officially, nothing happened. Unofficially, intelligence analysts are tearing the data apart looking for tactical implications. Is that paranoid? Maybe. But it's not implausible. Governments classify information all the time, especially information that could have military or strategic value. And a confirmed extraterrestrial detection absolutely has strategic value. It changes the threat landscape. It changes assumptions about what's possible technologically. It changes the geopolitical calculus. If one nation has access to that information and others don't, that's an intelligence advantage. And nations don't give up intelligence advantages voluntarily. There's also the jamming and disinformation angle. Suppose a detection is made public. The data is released. Independent researchers start analysing it. But then conflicting claims emerge. Some analysts say the signal is artificial. Others say it's a known pulsar. Still others suggest it's terrestrial interference, maybe from a satellite or a classified military transmission. The signal becomes contested. Nobody knows what to believe. And in that confusion, the truth gets lost. Now, who benefits from that confusion? If you're a government that doesn't want a detection confirmed, muddying the waters is a viable strategy. You don't have to prove it's not aliens. You just have to create enough doubt that consensus collapses. Release competing analyses. Fund studies that support the natural explanation. Leak information suggesting the original researchers made an error. You don't need to control the narrative completely. You just need to make sure nobody else can control it either. The protocol's no-reply clause could be interpreted as license for this kind of behaviour. If no official reply is allowed until consultation is complete, and consultation takes months or years, then during that window the information environment is fluid. It can be shaped, it can be controlled, and the public never gets a clear answer about what was detected or what it means. Now let's talk about the private sector. Tech companies and space startups are increasingly involved in space activities. They launch satellites, they operate ground stations, they have access to data streams and observational capabilities that rival or exceed traditional scientific institutions. What happens if one of these companies detects something? Do they follow the protocol, or do they go public immediately? Maybe because publicity drives stock prices or attracts investment. Corporate incentives don't always align with scientific norms or international governance. A startup might see a detection as a branding opportunity. A tech giant might see it as a chance to position itself as the leader in extraterrestrial communication. And if they decide to broadcast a reply without authorization, what's anyone going to do about it? Sue them? Sanction them? The protocol has no enforcement mechanism for private actors, especially private actors with resources and legal teams. Let's circle back to 3I-ATLAS. If its anomalies are flagged as possibly artificial, how do defense and intelligence communities respond? Do they monitor the object? Do they task satellites and ground-based sensors to track it continuously? Do they classify the findings? We don't know, because that kind of activity doesn't show up in press releases. But it's reasonable to assume that if an interstellar object is behaving strangely, someone in a windowless building somewhere is paying very close attention. And if they find something, if classified analysis reveals something the public isn't told, then the protocol becomes a convenient cover. We're consulting, we're verifying, we're waiting for international consensus. Meanwhile, the real decision-making happens behind closed doors, in classified briefings, among people who never have to justify their conclusions publicly. The protocol frames that secrecy as scientific caution, but it could just as easily be strategic control. Here's the uncomfortable question. If national security enters the picture, where does the line between caution and control sit? When does prudence become suppression? When does governance become gatekeeping? The protocol doesn't answer that. It can't. Because the protocol is an advisory document written by scientists, and scientists don't control classified information. Governments do. So what we're left with is a framework that works well if everyone plays by the rules, but breaks down the moment someone decides the rules don't apply to them. And in a domain where the stakes include national security, corporate competition, and geopolitical advantage, the assumption that everyone will play by the rules is optimistic at best. The protocol's attempt to manage this is transparency, open data, independent verification, multidisciplinary review. The idea is that if information is public, it's harder to suppress or manipulate. But transparency has limits. It doesn't apply to classified programs. It doesn't constrain private actors who aren't bound by scientific norms. And it doesn't prevent disinformation campaigns designed to create confusion rather than clarity. Here's the final piece. If the protocol's no-reply clause is invoked, there's a window, maybe a long one, where only insiders know what's happening. The public sees we're consulting. But insiders see data, analysis, strategic assessments, contingency plans. And during that window, decisions get made. Decisions about what to say, who to tell, how to frame the information. Decisions that shape the narrative before most people even know there's a narrative to shape. Governance for contact isn't just academic. It sits at the intersection of science, intelligence, and power. And when those three things converge, the risk isn't just that we'll get the science wrong. The risk is that the science will be right, but the response will be determined by interests that have nothing to do with truth or transparency. The protocol frames itself as a mechanism for caution, but it could just as easily be a mechanism for secrecy, and telling the difference from the outside might be impossible. Part 9. The 3I Anomalies Dossier. Chemistry, Physics, and Weird Behaviour. Let's get specific. Let's talk about what makes 3I-ATLAS so strange that it's captured the imagination of scientists and conspiracy theorists alike. Because the object isn't behaving like a typical comet. The data coming back from our best instruments is full of anomalies, things that don't quite fit. And while anomalous doesn't mean artificial, it does mean we're dealing with something we don't fully understand. So let's go through the dossier point by point and see what we're actually looking at. First, the chemistry. The James Webb Space Telescope has been observing 3I-ATLAS since late July 2025, capturing spectra of the gases being released from the object's surface. What they found is unusual. The coma, the cloud of gas and dust surrounding the nucleus, is dominated by carbon dioxide. That's not unheard of in comets, but the ratio is extreme. The carbon dioxide to water ratio is approximately 8 to 1, plus or minus 1. That means for every water molecule being released, there are 8 carbon dioxide molecules. Most comets show the opposite pattern. Water is the primary volatile, with carbon dioxide as a minor component. 3I-ATLAS flips that script entirely. Why does this matter? Because the composition of a comet tells you about where and how it formed. Comets are frozen time capsules, preserving the chemistry of the molecular cloud that spawned them. Our solar system's comets formed in a region dominated by water ice, with smaller amounts of carbon dioxide, methane, ammonia, and other volatiles. But 3I-ATLAS came from somewhere else. A different star system, a different molecular cloud, and apparently that cloud had very different chemistry. High carbon dioxide, low water, that's plausible. Molecular clouds vary. but it's the first time we've seen it in an interstellar object, and it raises questions about what kind of environment could produce that signature. Next, the polarimetry. Ground-based observatories have been measuring how light scatters off 3I-ATLAS, and the results are unprecedented. The object shows a deep negative polarization branch, meaning the way light is polarized after scattering is unusual. The inversion angle, the point where the polarization changes sign, is around 17 degrees. That's a signature astronomers haven't seen in any known comet. Polarization tells you about the properties of the particles doing the scattering. Size, shape, composition, all of these affect how light bounces off dust grains and gas molecules. Normal comets have polarization signatures that match models based on irregular silicate grains mixed with organic compounds. But 3I-ATLAS doesn't match those models. Its polarization suggests the particles in its coma have properties we haven't encountered before. Maybe they're a different size distribution. Maybe they're a different composition. Maybe they're structured in ways that natural dust grains typically aren't. We don't know, but it's weird. Then there are the metallic emission claims. This is where things get speculative because the data here is less solid. Some reports, primarily from tabloid sources citing preliminary spectroscopic observations, suggest that 3I-ATLAS is emitting metallic compounds, specifically nickel alloys, at a rate of about 4 grams per second, without detectable iron. If true, that would be extraordinary. Natural comets don't emit refined metals. They can have trace metals in their dust, but not in the form of alloys and not at emission rates that high. But we have to be careful here. These claims haven't been peer-reviewed. They haven't been confirmed by independent observatories. They're based on spectral lines that could have multiple interpretations. Spectroscopy is tricky. You're looking at light that's been absorbed or emitted by atoms and molecules, and you're trying to figure out what those atoms and molecules are. But lines can overlap. Instruments can produce artifacts. And without rigorous analysis, it's easy to misidentify features. So the metallic emissions are intriguing, but unverified. They're a data point that demands follow-up, not a conclusion. If subsequent observations confirm the presence of nickel alloys, then we have a real problem, because that would be very hard to explain naturally. But until that confirmation happens, we treat it as a possibility, not a fact. Now, let's talk about behaviour. 3I-ATLAS wasn't showing a typical comet tail in early observations. Comets develop tails as they approach the Sun because solar radiation heats their surfaces, causing volatiles to sublimate and carry dust particles away from the nucleus. The pressure of sunlight and the solar wind push this material into a tail that points away from the Sun. It's one of the most recognizable features of comets. But 3I-ATLAS was initially quiet. No prominent tail, just a faint coma. That's unusual for an object approaching perihelion, but not impossible. Maybe the surface hadn't heated up enough yet. Maybe the volatiles were buried under a layer of refractory material. But then, in late August, the Keck Observatory detected an anti-tail, a feature that appears to point toward the Sun rather than away from it. Anti-tails are optical illusions. They occur when larger, heavier particles are ejected from the comet and lag behind in its orbit. From our viewing angle, those particles can appear to form a tail pointing in the wrong direction. It's rare, but it happens. The most famous example is Comet Arend-Roland in 1957, which displayed a prominent anti-tail, so the feature itself isn't evidence of anything extraordinary. But combined with everything else, the quiet early behaviour followed by the sudden appearance of an anti-tail adds to the sense that this object is unpredictable. So let's step back and ask the big question. Could all of these anomalies be explained by natural processes? Yes, absolutely. Interstellar objects come from environments we've never sampled directly. Their chemistry could be exotic but still natural. Their dust properties could reflect formation conditions we don't encounter in our own solar system. The metallic emissions, if they're real, could be a byproduct of surface chemistry we haven't seen before. The behavioural oddities could be due to an unusual rotation state or internal structure. Natural explanations exist for every single data point. But here's the problem. When you stack anomaly on top of anomaly, when every measurement comes back unexpected, at some point you have to ask, is this just a really weird comet, or is it something else? And that's the question scientists are grappling with right now. The what-if framing goes like this. What if 3I-ATLAS is a probe? An artifact sent from another civilization to explore other star systems? What would that look like? Well, it might look like a comet at first glance. It might have a protective coating of ice and dust to shield it from interstellar radiation. But up close, under scrutiny, it might show signs that don't quite fit. Chemistry that's too specific. Materials that don't occur naturally. Behaviour that suggests intent rather than chaos. We design our own spacecraft to survive harsh environments. We use ablative heat shields. We coat surfaces with protective materials. We engineer trajectories to maximise efficiency. If another civilization did the same, their probe might not announce itself. It might blend in until it got where it was going, and only then, if at all, would it reveal its true nature. Now, most scientists who've looked at the data still favour natural explanations. The consensus, if there is one, is that 3I-ATLAS is a comet, unusual but ultimately explicable by processes we understand or will understand once we have more data. And that's a reasonable position. Extraordinary claims require extraordinary evidence, and we're not there yet. The data is suggestive, but it's not definitive. But the anomalies raise the stakes. If the object is genuinely unusual, if further observations confirm that it doesn't fit any natural model, then the protocol's timing becomes more than coincidence. Because this is exactly the scenario the protocol is designed for. An object that might be artificial, ambiguous data, global attention, the need for consultation before anyone does anything rash. Whether 3I-ATLAS is natural or engineered, mundane or extraordinary, it's already serving as a test case, a test of our instruments, a test of our analytical capabilities, a test of our governance frameworks, and maybe, if we're lucky or unlucky depending on your perspective, a test of whether we're ready for contact. Because if this object is just the opening act, if there's more to come, then the decisions we make now will set the precedent for everything that follows. And we only get one chance to get this right. Part 10. Conspiracy Cartography. Who benefits from secrecy? Let's map the terrain. You've got a revised protocol with a no-reply clause. You've got an interstellar object with unexplained anomalies. You've got global attention and conflicting narratives. And underneath it all, you've got a question that won't go away. Who benefits if the story stays quiet? Because that's the question conspiracy theories are built on. Not evidence, but motive. And if you're going to understand why these theories have traction, you need to understand the motives people are attributing to different actors in this scenario. Let's start with the stakeholders. First, the scientific community, specifically the International Academy of Astronautics and SETI researchers. What do they gain from the protocol and from how the 3I-ATLAS story is being told? Credibility, for one. If they handle a potential detection properly, if they follow rigorous procedures and avoid premature claims, their reputation is enhanced. Funding, for another. High-profile detections, even ambiguous ones, attract public interest, which attracts funding. So scientists have an incentive to be cautious, to follow the protocol, to avoid the embarrassment of crying alien when it's just a comet. But they also have an incentive to make discoveries. Careers are built on breakthroughs. Nobel Prizes are awarded for paradigm shifts, so there's a tension. Be cautious, but not so cautious that you miss something extraordinary. That tension creates space for disagreement within the scientific community, and those disagreements can be exploited by people looking for cracks in the official story. Next, the United Nations and space governance bodies like UN COPIOS. What do they gain? Authority. If the protocol is followed, if consultation happens through official channels, then the UN becomes the central node in the most important conversation humanity has ever had. That's soft power on a scale we've never seen. It legitimizes the UN's role in space governance at a time when that role is being challenged by private companies and nationalist space programs. So the UN has an incentive to ensure the protocol is followed, to make sure that any detection or response goes through them. But they also have an incentive to avoid chaos. If a detection happens and the public panics, if markets crash, if social order breaks down, that's a governance failure. So the UN might prefer to manage information carefully, to release details slowly, to frame the narrative in ways that minimize disruption. And that preference for stability can look a lot like suppression if you're inclined to see it that way. Now, nation-states, governments have complex and sometimes competing incentives. Security and control are obvious ones. If a detection has strategic implications, if it changes the threat landscape or reveals new technologies, governments want to control that information. They don't want adversaries to have it. They don't want the public to panic. They don't want to lose the advantage that comes from knowing something others don't. But governments also have to manage domestic politics. If citizens believe their government is hiding information about extraterrestrial contact, trust erodes. Legitimacy erodes. So there's a balancing act. Control the information, but don't appear to be controlling it so tightly that people revolt. That's a difficult line to walk, and different governments will walk it differently depending on their political cultures and institutions. Private observers and citizen scientists have different incentives entirely. They gain independence, credibility, audience. If a private group makes a detection and publicises it, they become famous. They bypass the traditional gatekeepers. They prove that you don't need a government grant or a university affiliation to contribute to humanity's biggest questions. So private actors have an incentive to go public quickly, to bypass the protocol, to claim credit before anyone can tell them to stay quiet. But they also face risks. If they're wrong, if their detection turns out to be a false positive, their credibility is destroyed. So even private actors have reasons to be cautious, to verify, to follow at least some of the protocol's procedures, even if they don't strictly have to. Then there's alternative media and live streamers. Their incentives are straightforward. Audience and clicks. Conspiracy theories generate views. Drama generates engagement. If the story is scientists are being careful and following procedures, that's boring. But if the story is governments are hiding evidence of aliens, that's compelling. It's shareable. It goes viral. So alternative media has an incentive to frame every ambiguity as evidence of a cover-up, every delay as evidence of suppression. Now let's map out some hypotheses. Hypothesis 1. Honest precaution. The authorities, scientific and governmental, genuinely want to avoid premature hype or public panic. They know false alarms have happened before. They know the consequences of getting it wrong. So they're following established procedures, being cautious, waiting for more data before making any definitive claims. Under this hypothesis, the protocol is what it claims to be, a framework for responsible governance. Hypothesis 2. Bureaucratic capture. The protocol is being used by governments and international bodies to keep decision-making centralized, not because there's a specific secret to hide, but because institutions prefer control. They prefer to manage narratives, to coordinate responses, to ensure that no rogue actor disrupts the process. Under this hypothesis, the protocol serves institutional interests more than public interests, but there's no grand conspiracy. Just bureaucracy doing what bureaucracy does. Hypothesis 3. Stage test. The protocol and 3I-ATLAS are both part of a dry run. Authorities know or suspect that contact is coming, maybe not from this object, but soon, and they're using this event to test systems to see how information flows, how the public reacts, how different actors behave. Under this hypothesis, 3I-ATLAS is significant, but its significance is in what it reveals about our readiness, not necessarily about the object itself. The protocol isn't reactive, it's preparatory. Hypothesis 4. Real secrecy. Something has been discovered about 3I-ATLAS, or something was discovered before it, that the public isn't being told. Maybe the object's anomalies are more extreme than what's been reported. Maybe there's been communication, a signal, something that definitively marks it as artificial. Maybe classified observations have revealed features that can't be explained naturally, and the protocol's consultation phase is actually a cover for closed-door decision-making about how to respond. Under this hypothesis, the public narrative is sanitized. The real story is classified. Now let's evaluate these hypotheses against the evidence we have. For honest precaution, the evidence is the documented timeline of the protocol revision, the public availability of data, the involvement of multiple independent observatories, and the absence of leaked information suggesting a cover-up. Scientists are doing what they say they're doing, observing, analysing, debating. That's consistent with normal scientific practice. Against honest precaution is the timing. The protocol drops right as 3I-ATLAS arrives. The no-reply clause appears just when we might need it. That's either remarkable foresight or remarkable coincidence, and coincidences make people suspicious. For bureaucratic capture, the evidence is the structure of the protocol itself, which centralizes authority in bodies like the IAA and UN COPUOS. The protocol explicitly prevents individual or organizational responses without consultation. That's control, formalized, and institutions have a long history of preferring control over chaos, even when that preference serves their interests more than the public's. Against bureaucratic capture is the transparency. The protocol is public. The data from 3I-ATLAS is being published in academic papers. Live streams are dissecting every detail. If this were pure bureaucratic gatekeeping, you'd expect more information. Suppression, not less. The fact that we're having this conversation at all suggests the gates are more open than closed. For the stage test hypothesis, the evidence is circumstantial. The protocol's emphasis on procedures, coordination, and communication management does read like a dress rehearsal. If you were planning for future contact scenarios, you'd want to test your systems on something real but manageable. 3I-ATLAS fits that profile. It's unusual enough to trigger attention, but not so extraordinary that it forces immediate action. It's ambiguous, which means you can observe how different actors interpret ambiguity and respond to it. Against the stage test is lack of direct evidence. We don't have documents saying use 3I-ATLAS as a test case. We don't have whistleblowers confirming it. It's a theory that fits the facts, but so do other theories, and without more it remains speculation. For real secrecy, the evidence is the absence of evidence. We don't see classified observations. We don't know what defense and intelligence agencies are doing behind the scenes. We don't have access to the full dataset, only what's been published. If something extraordinary has been found, and if that information is classified, we'd never know. By definition, successful secrecy is invisible, but against real secrecy is the difficulty of maintaining it. Modern astronomy is global. Observatories are distributed across continents. Data is shared widely. Keeping something truly extraordinary secret would require coordinating dozens or hundreds of institutions and thousands of individuals across multiple countries. That's hard. Leaks happen. Whistleblowers come forward. The bigger the secret, the harder it is to keep. And so far, we haven't seen credible leaks suggesting 3I-ATLAS is anything other than what's been publicly reported. So where does that leave us? With uncertainty. Each hypothesis has supporting evidence. Each has weaknesses. And that uncertainty is where speculation thrives. Because when people don't know what's true, they fill the gaps with narratives that fit their priors. If you trust institutions, you lean toward honest precaution. If you're skeptical of power, you lean toward bureaucratic capture or real secrecy. If you think we're at a turning point in history, you lean toward the stage test. Your interpretation says as much about you as it does about the facts. Now, let's talk about who benefits from secrecy, because that's the heart of the conspiracy framework. If there is a cover-up, who gains? Governments gain time to prepare, to strategize, to position themselves advantageously. They gain control over the narrative, which means control over how populations react. They avoid panic, chaos, economic disruption, at least in the short term. But they also risk losing legitimacy if the truth eventually comes out and people realize they were misled. Private interests might gain if contact or detection leads to new technologies, new markets, new opportunities. If a corporation gets access to extraterrestrial data or artifacts before their competitors, that's a massive advantage. So corporate actors might have incentives to suppress information that would level the playing field or trigger regulatory scrutiny. Alternative media gains audience and influence by positioning themselves as truth-tellers against official lies. Every delay, every ambiguity, every refusal to answer a question becomes evidence of conspiracy in their narrative. And that narrative attracts people who already distrust institutions, creating a self-reinforcing loop. But here's the counter-argument. Who benefits from transparency? Scientists benefit because open data means better science, more collaboration, faster progress. The public benefits because information allows informed decision-making, reduces fear of the unknown, and builds trust in institutions. Humanity as a whole benefits because if we're going to respond to extraterrestrial contact, or even the possibility of it, we need collective buy-in, we need consensus. And you can't build consensus on secrets. So the tension isn't just between secrecy and transparency. It's between short-term interests and long-term ones. In the short term, secrecy might serve narrow interests. But in the long term, transparency is the only sustainable path. The question is whether the actors involved recognize that, or whether they're optimizing for their immediate needs at the expense of the future. Let me illustrate with a game theory scenario. Imagine two players, the public and the state. The state has information. The public wants information. The state can choose to share or withhold. The public can choose to trust or distrust. If the state shares and the public trusts, everyone wins. Information flows, decisions are made collectively, and legitimacy is maintained. If the state withholds and the public trusts, the state gains short-term control, but risks long-term exposure and loss of legitimacy. If the state shares and the public distrusts, you get chaos because the information is misinterpreted or rejected. And if the state withholds and the public distrusts, you get the worst outcome. No information, no trust, no cooperation. Right now, we're somewhere between those scenarios. The state, broadly defined to include scientific and governmental institutions, is sharing some information but not necessarily everything. The public, broadly defined, is split. Some trust, some distrust, and that split is driving divergent narratives. The protocol is trying to manage this by creating a structured process, but structure only works if people accept it, and acceptance requires trust. Which brings us back to the central problem. Trust is fragile, and once broken, it's very hard to rebuild. So who benefits from secrecy? In the short term, those who have power and want to keep it. In the long term, nobody. Because secrets revealed create backlash, and backlash destroys the institutions that tried to keep the secret in the first place. The only question is whether we're still in the short term, or whether we're approaching the moment when the long term catches up. Here's the final point. Speculation thrives because many questions remain unanswered. We don't know everything about 3I-ATLAS. We don't know what's been discussed in closed-door meetings. We don't know what observations are classified. We don't know what decisions have been made about how to respond if the object turns out to be extraordinary. And in the absence of answers, people construct their own. Some of those constructions are reasonable extrapolations, some are paranoid fantasies, and most are somewhere in between. Motive does not equal proof. The fact that someone would benefit from secrecy doesn't mean secrecy is happening. The fact that the timing is suspicious doesn't mean it's intentional. The fact that institutions have power doesn't mean they're abusing it. But it also doesn't mean they're not. And that ambiguity, that space between what we know and what we suspect, is where the conspiracy lives. Not in evidence, but in the gaps. And until those gaps are filled, the conspiracy will persist. Because there are plausible reasons for secrecy, just as there are plausible reasons for transparency. And the truth, as always, probably lies somewhere in the middle, which is the most unsatisfying answer possible, but also the most likely one. Part 11. JWST's little red dots. Are we seeing the first black hole stars? Let's shift gears for a moment and talk about something that, at first glance, seems completely unrelated to 3I-ATLAS, but actually matters quite a bit when you think about detection, governance, and what counts as extraordinary. Because while the protocol revision and the interstellar object have been capturing headlines, the James Webb Space Telescope has been quietly finding things in deep space that don't fit our models, things that challenge our assumptions about what's natural, what's possible, and how we distinguish between the two. The latest puzzle, little red dots, that's what astronomers are calling them, ultra-compact, ultra-red objects detected in JWST infrared images of the early universe. They're bright, they're small, and their spectral signatures suggest they might be black holes embedded inside stars, a configuration so exotic that it barely makes sense. But if the observations hold up, if these things are real, then we're seeing a class of objects we didn't know could exist, and that has implications. Here's what the data shows. These objects are incredibly compact, smaller than typical galaxies, but far brighter than individual stars. Their colour profiles are redder than almost anything else in the images, which suggests they're either extremely dusty or extremely redshifted or both. When astronomers analyse their spectra, they see emission lines that don't quite match any known category. Not normal stars, not normal galaxies, not normal black holes, something in between, or something entirely new. One hypothesis is that these are black hole host stars, theoretical objects where a black hole exists at the centre of a massive star, accreting material from the star's core and radiating energy outward. This configuration should be unstable, short-lived, maybe impossible. But the data suggests they exist, at least in the early universe. If true, that's a fundamental expansion of what we thought was astronomically possible. Now, why does this matter for 3I-ATLAS and the protocol? Because it changes our benchmark for what counts as weird. Before JWST we had models. We knew what stars should look like, what galaxies should look like, what black holes should look like. And when we saw something that didn't fit those models, we had two options: expand the models or consider non-natural explanations. But JWST is showing us that the universe is stranger than our models predicted. Natural phenomena we didn't anticipate. Configurations we thought were impossible. Chemistry and physics operating in ways we hadn't imagined. That means the threshold for extraordinary is higher than we thought. If black hole stars can exist naturally, if ultra-compact red objects are just a new category of astrophysical phenomena, then detecting something weird isn't enough to conclude it's artificial. You have to rule out all the natural explanations, including the ones you haven't thought of yet, and that's harder than it sounds. Here's the analogy. Imagine you're driving on a road, and you see something in the distance that doesn't look like any vehicle you've ever seen. It's hovering. It's silent. It's moving in ways that defy your understanding of aerodynamics. Your first thought might be, that's not natural. That's technology. But then you learn about a new type of drone, or a new aircraft design, or a rare atmospheric phenomenon that creates optical illusions. Suddenly, the threshold for concluding alien spacecraft is much higher, because you have more natural explanations to rule out first. JWST is expanding our catalogue of natural phenomena faster than we can update our intuitions. Every deep field image reveals structures we didn't expect. Every spectroscopic analysis finds molecules in places they shouldn't be. Every observation challenges some assumption we thought was solid, and that's wonderful for science. It means we're learning. But it also complicates detection frameworks, because the more we learn about what's naturally possible, the harder it becomes to identify what isn't. Now, apply this to technosignature searches. The protocol emphasizes multidisciplinary review precisely because anomalies can have multiple explanations. A spectral line you think is industrial emission might be exotic chemistry. A polarization signature you think is artificial might be a new type of dust grain. A trajectory you think is evidence of propulsion might be a gravitational interaction we didn't model correctly. JWST is proving that the universe is full of surprises, and most of those surprises are natural. But here's the flip side. If natural phenomena are stranger than we thought, then distinguishing artificial from natural becomes blurrier. It's not impossible, but it requires more data, more rigor, more time. And time is something the protocol tries to buy by imposing the no-reply clause. Because if you detect something ambiguous and you respond immediately, you might be responding to a natural phenomenon you misidentified. But if you wait, if you verify, if you rule out all the natural explanations, including the ones you just learned about from JWST, then your response is informed, it's deliberate, it's less likely to be embarrassing or dangerous. So JWST's little red dots matter because they remind us that our ignorance is vast. We're still discovering basic categories of objects in the universe. We're still expanding our understanding of what's possible naturally, and that expansion is ongoing. It's not like we'll reach a point where we know everything and can confidently say, okay, now anything beyond this must be artificial. We're always going to be on the frontier of knowledge, always discovering new natural phenomena that challenge our assumptions, and that brings us to the governance question. If our baseline for normal keeps shifting, how do we write rules about detecting abnormal? The protocol tries to handle this by requiring verification and consultation, but it can't account for unknown unknowns. It can't anticipate the next discovery that redefines the possible. So governance has to be flexible, adaptive, willing to update as our knowledge expands. Here's a speculative angle. Could future little red dots trigger the protocol's reply/no-reply question? Probably not directly, because they're billions of light years away. We're seeing them as they were in the early universe, long before Earth existed. But what if JWST finds one nearby? What if a compact infrared source with anomalous spectral features is detected in our own galaxy, or even in our own solar system? At what point does a detection shift from interesting science to potential technosignature? The answer depends on context, distance, behaviour, composition, repeatability. All of these factor into the assessment. A little red dot 13 billion light-years away is fascinating but not actionable. A similar object 100 light-years away displaying modulation or directionality might be, and a similar object passing through our solar system showing chemistry that doesn't match any known natural source definitely would be. 3I-ATLAS sits in that middle zone. It's here, it's close, it's anomalous. But is it anomalous enough to invoke the protocol's full machinery? That depends on how the anomalies hold up under scrutiny, how many natural explanations can be ruled out, and how confident we are in the remaining assessments. JWST's discoveries remind us that ruling out natural explanations is an ongoing process, not a one-time check. So the lesson is this: as the cosmos reveals stranger natural phenomena, our distinction between natural and artificial becomes blurrier. We can't rely on intuition. We can't rely on models that are always being updated. We have to rely on process, on verification, on multidisciplinary review, on patience. And that's what the protocol is trying to enforce. Not because the scientists writing it are slow or overly cautious, but because they know how easy it is to be wrong. How many times in history we've seen something strange and jumped to conclusions that later embarrass us. Black hole stars, if they're real, are a perfect example of nature being weirder than fiction. They're objects that shouldn't exist according to older models, but apparently do according to newer data. And if nature can surprise us like that, if the universe can produce configurations we thought were impossible, then we have to approach every anomaly with humility. Because the universe doesn't care about our expectations. It is what it is, and our job is to figure out what that is, not to impose our assumptions on it. As our ability to detect strangeness increases, the need for solid governance processes grows, not to suppress discovery, but to manage it responsibly, not to silence voices, but to ensure that when we speak, when we respond, when we make claims about what we've found, those claims are grounded in the best available evidence and the most rigorous analysis. JWST is expanding our reach. The protocol is trying to ensure that our reach doesn't exceed our grasp. And whether it succeeds depends on whether we can balance curiosity with caution, ambition with humility, speed with rigor. That balance is hard. But if 3I-ATLAS teaches us anything, it's that we need it now more than ever. Part 12. Quantum Trick for Solar Power. Unlocking a 100-year-old quantum secret. While astronomers have been watching the sky, engineers have been rewriting the rules on the ground. One of those rule changes involves solar power, quantum mechanics, and a breakthrough that sounds obscure but has implications for how we detect, monitor, and respond to things like 3I-ATLAS. Because the story of technosignature detection isn't just about big telescopes and government agencies. It's also about who has access to the tools, who can afford to participate, and how quickly technology is democratizing observation. The breakthrough. Researchers have unlocked what they're calling a 100-year-old quantum secret, a method for dramatically improving solar cell efficiency using quantum effects that were predicted theoretically decades ago, but only recently engineered into practical devices. The details involve things like quantum tunneling, multi-junction cells, and hot carrier extraction. You don't need to understand the physics to grasp the implication. Solar power is about to get cheaper, more efficient, and more accessible. Why does that matter for space observation? Because power is the limiting factor for most sensor networks. You want to run a radio telescope? You need power. You want to operate a satellite constellation? You need power. You want to build a private SETI station in your backyard? You need power. And if power gets cheaper, if you can generate more electricity from smaller, lighter, more deployable panels, then suddenly the barrier to entry drops. More actors can participate. More sensors can be deployed. More data can be collected. Now let's think about this in concrete terms. Right now, large-scale SETI projects are dominated by institutions with significant funding, universities, government agencies, international collaborations. They have the resources to build and operate big dishes, to process vast amounts of data, to maintain observing campaigns that span years or decades. But what happens when a private group, maybe a startup, maybe a wealthy individual, can build a comparable capability for a fraction of the cost? What happens when sensor networks become so cheap that you can blanket a continent with them, creating a distributed detection system that no single institution controls? That's where governance becomes complicated. The protocol assumes a certain institutional structure. It assumes that detections will happen through recognized channels, that data will flow through established pipelines, that coordination will happen among known actors. But if technology democratizes observation, if detection capability becomes widely distributed, then the protocol's assumptions break down. Because you can't coordinate with everyone, you can't enforce notification requirements on thousands of independent operators, and you can't prevent someone from broadcasting a reply if they have the tools and the inclination to do it. This isn't hypothetical. We're already seeing the beginnings of this shift. Citizen science projects like SETI, at home, distributed computation, across millions of personal computers, allowing ordinary people to contribute to data analysis. Crowd-funded satellite projects like Planet Labs have put Earth observation capabilities into the hands of private companies. Amateur radio astronomers are detecting pulsars and mapping the sky with equipment they built in their garages. The tools are getting better and cheaper every year, and now, with advances in solar power, the energy constraint is loosening. You can deploy sensors in remote locations without needing grid power. You can operate continuously without worrying about fuel costs or battery life. You can scale up without proportionally scaling up your infrastructure budget. That's a game changer. Now tie this back to 3I-ATLAS. Imagine a private group, equipped with quantum-enhanced, solar-powered sensors detects an anomaly in the object's emissions. Maybe it's a faint radio signal. Maybe it's an optical pulse. Maybe it's a particle signature that doesn't match the official observations. Under the protocol, they're supposed to notify the IAA, archive their data, and wait for consultation. But what if they don't? What if they decide to go public immediately, or worse, to send a reply on their own? The protocol has no enforcement mechanism for this scenario. It can't confiscate their equipment. It can't silence their broadcasts. It can't prevent them from uploading their findings to the internet where millions of people will see it within minutes. And once information is out there, once it's viral, you can't put it back in the bottle. The consultation process becomes moot. The narrative is already shaped. The world is already reacting. Some people will see this as a feature, not a bug. Democratization means accountability. It means no single institution can control the story. It means transparency is enforced by the sheer number of observers, each acting as a check on the others. If something extraordinary is detected, the world will know, regardless of what governments or international bodies want. But others will see this as a threat to coordinated response. If anyone can detect and anyone can reply, then humanity doesn't speak with one voice. We speak with millions of voices, some informed, some reckless, some well-intentioned, some malicious. And that cacophony could be dangerous. Because if you're trying to communicate with an extraterrestrial intelligence, or even just study an interstellar object, consistency matters, clarity matters, and you can't have clarity when everyone is broadcasting their own message. There's also the false positive problem. Faster technology means faster detection, but it also means faster mistakes. If a private operator detects something and publishes without rigorous verification, and it turns out to be a satellite glint or an instrument artifact, the damage is done. Public trust erodes. Future claims are met with skepticism. The signal-to-noise ratio in the information environment gets worse, not better. The protocol tries to address this by emphasizing verification, peer review, and multi-observatory confirmation. But those processes take time, and time is exactly what faster technology compresses. If you can detect something in minutes and publish it in seconds, the verification process can't keep up. The old model of careful, deliberate analysis gives way to real-time information warfare, where the first claim shapes the narrative regardless of whether it's accurate. Here's the broader point. When technology becomes cheap and ubiquitous, governance can't rely on centralized control. It has to rely on distributed norms, on a shared understanding of best practices, on cultural expectations about responsibility and verification. The protocol is a step in that direction. It's an attempt to establish those norms, but norms only work if people buy into them, and if people don't trust the institutions promoting the norms, they'll ignore them. So the quantum solar breakthrough, and all the other technological advances happening right now, are accelerating a shift that the protocol is struggling to manage. The shift from centralized institutional observation to distributed, democratized observation, from gatekeeping to open access, from slow, deliberate analysis to fast, real-time response. That shift has enormous benefits. It makes science more inclusive, more transparent, more resilient to institutional failure. But it also has risks. It makes coordination harder, verification slower, and mistakes more likely. And when you're dealing with something as consequential as potential extraterrestrial contact, those risks matter. Because the decisions we make, the messages we send, the responses we choose, they're not just about us. They're about humanity as a whole. And if those decisions are being made by whoever has the fastest equipment and the loudest megaphone, rather than through careful, collective deliberation, then we're risking outcomes nobody wants. The protocol is an attempt to navigate this tension, to balance speed with rigor, to balance access with coordination, to balance individual freedom with collective responsibility. Whether it succeeds depends on whether people see the protocol as legitimate, as serving their interests as worth following even when it's inconvenient. And that legitimacy can't be imposed. It has to be earned. Through transparency, through inclusion, through demonstrating that the process works and produces outcomes that are better than the alternatives. The tools exist. The framework exists. The question is whether we have the wisdom to use them well, or whether technology will outpace governance and leave us scrambling to manage consequences we didn't anticipate. 3I-ATLAS is a test case, and the test isn't just about the object, it's about us. About whether we can coordinate when it matters, about whether speed and access make us stronger or just more chaotic. The answer, as always, depends on what we choose to do next. Part 13, JWST finds carbon compounds in LMC ice. Implications for life detection. Let's talk about life. Not intelligent life, not necessarily, just life. Because while everyone's focused on technosignatures and interstellar probes, the James Webb Space Telescope has been finding something equally profound. The building blocks of life, frozen in ice clouds in the Large Magellanic Cloud, a satellite galaxy 160,000 light-years away. And those findings have implications for how we think about detection, about what we're looking for, and about how the protocol should handle ambiguities between technology and biology. The discovery, JWST detected complex carbon compounds in icy grains surrounding young stars in the Large Magellanic Cloud. We're talking about molecules like polycyclic aromatic hydrocarbons, organic compounds that are precursors to the chemistry of life as we know it. These compounds have been found before in our own galaxy, in molecular clouds and planetary systems closer to home. But finding them in another galaxy, in environments that are chemically different from our own, tells us something important. The ingredients for life are universal. They form naturally wherever the conditions are right. This matters because biosignature science, the search for signs of life, is advancing rapidly. We're moving beyond just looking for oxygen or methane in exoplanet atmospheres. We're looking for chemical disequilibria, combinations of gases that shouldn't coexist unless something is producing them. We're looking for surface features that might indicate biological activity. We're looking for patterns in light curves that might suggest vegetation or microbial mats. The scope of what counts as a potential biosignature is expanding, just like the scope of technosignatures. But here's where it gets complicated. Biology and technology aren't always easy to distinguish. A biosignature and a technosignature can look similar. Oxygen in an atmosphere could be produced by photosynthetic organisms, or it could be produced by industrial processes. A modulated radio signal could be a natural maester amplified by biological processes, or it could be an intentional transmission from a technological civilization. The lines blur, especially at the limits of our detection capabilities. And that blurring has implications for governance. The protocol talks about technosignatures, about detecting evidence of technology. But what if we detect evidence of life that isn't technological? What if we find biosignatures on an exoplanet, or in an interstellar object, or in samples returned from Mars? Does the protocol apply? Should we reply to a biosphere the same way we'd reply to a civilization? These questions aren't addressed explicitly in the current draft, and they need to be. Let's think about 3I-ATLAS through this lens. What if the object's anomalies aren't technological? What if they're biological? What if 3I-ATLAS is carrying prebiotic or even biotic material from another star system, material that's producing the unusual chemistry we're seeing? The high carbon dioxide ratio, the exotic polarization signature, even the unverified metallic emissions, all of these could potentially be explained by biological processes we've never encountered before. Panspermia, the idea that life can spread between star systems via comets and asteroids, is a legitimate scientific hypothesis. If microbes or organic compounds can survive the journey through interstellar space, embedded in ice and shielded from radiation, then interstellar objects like 3I-ATLAS are potential carriers. They could be seeding star systems with the raw materials for life, or even with life itself. And if that's the case, then detecting biosignatures in 3I-ATLAS wouldn't just be scientifically interesting, it would be paradigm shifting. But it would also raise the reply question in a new way. Do you reply to a comet full of microbes? Probably not. There's no intelligence there to communicate with. But what if the biosignatures are ambiguous? What if they could be biological or technological, and you can't tell which? The protocol's consultation mechanism is designed for this kind of ambiguity, but it assumes the ambiguity is about whether something is natural or artificial in a technological sense. It doesn't fully address the possibility of detecting life that isn't intelligent. The draft protocol does mention multidisciplinary review, which would include biologists and astrobiologists. So there's at least an acknowledgement that life detection is part of the picture. But the emphasis is still on intelligence, on communication, on the question of reply. And that emphasis might be too narrow, because if we detect life, even non-intelligent life from beyond Earth, that's one of the most profound discoveries in human history. And how we respond to it, how we study it, how we protect it or interact with it, those are questions that deserve the same level of careful governance as the technosignature question. Here's a scenario. JWST data from 3I-ATLAS reveals organic compounds that don't match any known abiotic process. Amino acids in ratios that suggest biological origin. Isotopic signatures that point to metabolic fractionation. Morphologies in the dust grains that look like fossilized microstructures. None of this is definitive. It's all ambiguous, open to interpretation, subject to debate. But it's suggestive enough that you can't dismiss it. Under the protocol, this detection would trigger consultation. The IA subcommittee would review the data. Biologists, chemists, geologists, astrobiologists would all weigh in. The conclusion might be, we don't know. It could be life. It could be exotic chemistry. We need more data. And in that state of uncertainty, do you attempt communication? Do you send a message to 3I-ATLAS on the off chance there's something intelligent aboard, or something that could interpret a signal? Or do you treat it as a scientific sample, something to study passively without attempting interaction? These aren't easy questions, and they illustrate why the protocol needs to evolve, because the universe of things we might detect is broader than just radio beeps from alien civilizations. It includes biosignatures, chemical anomalies, physical structures, behaviours that don't fit our models, and each category requires its own set of guidelines, its own decision-making framework. The JWST discovery of carbon compounds in the Large Magellanic Cloud tells us that life's building blocks are everywhere. That means life itself might be common, even if intelligent life is rare. And if life is common, then the probability of detecting it increases. We might find biosignatures on exoplanets. We might find them in our own solar system, on Mars or Enceladus or Europa. We might find them in interstellar objects passing through our neighbourhood. And when we do, we'll need rules about how to respond. Rules that account for the difference between biology and technology, between intelligence and mere chemistry. The protocol is a start, but it's incomplete. It focuses on the scenario where we detect a signal, something intentional, something that demands a reply. It's less clear about scenarios where we detect something ambiguous, something that might be life but might not, something that challenges our categories and forces us to think carefully about what we mean by contact and response. As our ability to detect life increases, the when to speak question becomes even more weighty. Because speaking to an intelligence is one thing, speaking to a biosphere is another, and knowing when you're doing, which is the hard part. The protocol tries to create space for that discernment, for consultation and review and multidisciplinary analysis. But it can only work if we expand our thinking beyond the classic SETI scenario, beyond the radio signal from a distant civilization, to include all the other ways life might reveal itself. And that expansion is necessary because the universe isn't going to fit neatly into our categories. It's going to surprise us. It's going to show us things we didn't anticipate, and we need to be ready to respond intelligently, whether what we've found is intelligent or not. So JWST's findings matter, not just because they tell us where life's building blocks are, but because they remind us that life detection is already relevant. It's not some far future possibility, it's happening now. And 3I-ATLAS, with all its anomalies, sits right at the intersection of these questions. Is it technological, biological, merely chemical? We don't know yet. But the protocol assumes we'll figure it out before we have to make any decisions about response. And that assumption might be optimistic, because sometimes the universe doesn't give us clear answers, it gives us ambiguity. And we have to decide how to act in the face of that ambiguity, knowing that whatever we choose carries consequences we can't fully predict. Part 14. Quantum computing rewrites the error bars. There is a new machine in the world now, and it thinks faster than anything we've built before. Quantum computers have crossed a threshold. They're no longer just theoretical toys locked in university labs. They're processing real data. They're solving real problems. And they're about to change everything about how we find things in space. In early 2025, researchers announced a breakthrough in quantum error suppression. The technical details don't matter as much as what it means. These machines can now run longer, more, stable calculations without collapsing into noise. They can simulate molecular interactions, optimize logistics networks, and most importantly for our story, they can chew through astronomical data at speeds that would make a traditional supercomputer look like it's standing still. NASA's Quantum Artificial Intelligence Laboratory has been testing applications for planetary science and exoplanet atmosphere modelling. The European Space Agency is exploring quantum algorithms for signal processing in radio astronomy. This isn't science fiction anymore, it's infrastructure. Here's why that matters for something like 3I-ATLAS. Traditional data analysis in astronomy is slow, painfully slow. You capture terabytes of images, spectra, radio signals. Then you spend months, sometimes years, running pattern recognition algorithms, filtering out noise, checking for instrumental artifacts, comparing against catalogues of known objects. A single high-resolution observation from the James Webb Space Telescope can take weeks to fully process and validate. The bottleneck isn't just computing power, it's the architecture of classical computing itself. You're running billions of sequential operations one after another, like reading a book one letter at a time. Quantum computing doesn't read sequentially. It explores multiple possibilities simultaneously. It can test thousands of hypothetical signal patterns at once, collapsing the answer only when it finds a match. What used to take a graduate student 6 months to analyse could theoretically be processed in days, maybe hours. Suddenly, amateur astronomers with access to cloud-based quantum platforms, which are starting to exist, can run analyses that once required institutional resources. A high school student in Jakarta could rent time on a quantum processor and scan through archived SETI data, looking for patterns that human researchers might have missed. The democratization of analysis power is already beginning. Here's a scenario that should worry you. A private quantum computing startup, let's call them something trendy like Quasar Analytics, offers a service to analyze archival comet data. They use a proprietary algorithm that claims to detect non-random patterns in outgassing behavior. Someone uploads all the available 3I-ATLAS observations. The algorithm flags a repeating pulse in the infrared emissions, something that looks, to the untrained eye, like a deliberate signal. The company publishes a blog post with charts and graphs. It goes viral on social media. News outlets pick it up. Within 12 hours, millions of people believe there's evidence of a probe inside 3I-ATLAS. But the analysis was flawed. The algorithm misinterpreted instrumental noise as signal. By the time professional astronomers debunk it, the narrative is already set. This is not hypothetical hand-waving. False positives in signal detection happen all the time. The famous WOW signal from 1977 was never confirmed. The periodic dimming of Tabby's star was initially thought to be alien megastructures, but was later explained by dust. The recent phosphine detection on Venus, announced in 2020, was later disputed by multiple teams who reanalyzed the data and found calibration errors. Each time, the initial announcement created a wave of excitement, followed by a wave of skepticism, followed by a quiet retraction that far fewer people paid attention to. Reputational damage doesn't just affect the researchers who got it wrong, it affects public trust in science itself. Now apply quantum speed to that cycle. If mistakes happen 10 times faster, does trust erode 10 times faster too? The draft protocol says no one should transmit a reply to a confirmed signal without international consultation. But what if independent actors, empowered by quantum tools, decide to respond on their own? What if a crowd-funded collective announces they're beaming a message to 3I-ATLAS before the IA subcommittee even meets? Speed doesn't just change detection, it changes governance. Let's go back to 3I-ATLAS specifically. The tail anomalies, the ones that made it so strange compared to Borisov, involved brightness fluctuations and spectral features that didn't quite match typical cometary behaviour. Some researchers proposed fragmentation, others suggested unusual volatile composition. A few quietly wondered if there was something else. Traditional analysis took months to sort through these possibilities. Quantum-accelerated analysis could revisit that data, test 1,000 fragmentation models in parallel, and either confirm the boring explanation or amplify the anomaly into something far more interesting. The question is, would speed lead us to truth or to overconfidence? Part 15. Nobel Prizes and the Architecture of Credibility. On October 7, 2025, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 researchers for their work on superconducting quantum circuits. The names don't matter as much as what they represent. They represent the peak of scientific credibility, the highest honour, the institutional blessing that transforms obscure research into global recognition. And with that recognition comes funding, influence, and the power to shape what the public believes is true. Prizes matter in science more than we like to admit. They're not just shiny medals, they're architecture. They define who gets listened to. They determine which institutions attract the best students, which projects get funded, which voices dominate the conversation when something strange appears in the sky. When an astronomer from a Nobel-winning institution says a comet is just a comet, people believe them. When a researcher from a small university in Kazakhstan says the same comet might be something else, people scroll past. This isn't conspiracy, it's sociology. Credibility is built on networks of trust, and those networks are centred around institutions, the International Astronomical Union, NASA, the European Space Agency, the Max Planck Institute, Caltech, MIT. These are the places where consensus is forged, where data is validated, where the official story gets written. And when something like 3I-ATLAS appears, something that doesn't quite fit the models, the official story becomes the battleground. Let's be clear about what's at stake. When the James Webb Space Telescope captures an image, or when the Hubble detects an anomaly, the data goes through layers of institutional review before the public sees it. There are calibration checks, cross-referencing with existing catalogues, peer review processes that can take months. This isn't censorship, it's rigor. But it also means that the first people to define what something is are the people inside those institutions, the people with the credentials, the people with the Nobel Prizes on their walls. But what happens when those institutions disagree with independent researchers? What happens when a private astronomer, someone with no institutional affiliation, analyses publicly available data and comes to a radically different conclusion? The draft protocols we've discussed emphasise transparency, open data, subcommittee oversight. These are good principles, but they also assume that everyone agrees on what the data means. History suggests otherwise. Think about the UFO debate, which has shifted dramatically in the past 5 years. For decades, institutional science dismissed UFO reports as misidentifications, hoaxes, or psychological phenomena. The credibility gap was enormous. Then the US government released Navy footage of unidentified aerial phenomena. Suddenly the conversation changed. Not because the evidence became more compelling, but because the source became more credible. An official Pentagon release carries weight that a civilian video never could, even if they show the same thing. Now imagine that dynamic playing out with 3I-ATLAS. Suppose the object makes its close approach in late 2025, and someone captures an unusual signal. A private researcher, someone with access to a mid-sized telescope and quantum-accelerated analysis software, publishes a paper claiming the signal is non-natural. They post it online, bypassing traditional peer review. Within hours, it's trending. The media picks it up. Public interest explodes. Then, 3 days later, a consortium of institutional astronomers releases a statement. They've analysed the same data. Their conclusion: instrumental artifact, natural phenomenon. Nothing to see here. Who does the public believe? The lone voice or the chorus of authority? The answer depends on how the message is delivered. If the institutional response feels defensive, if it arrives late, if it invokes classification or restricted data, then public trust fractures. People start asking why the delay. What are they hiding? The protocol's emphasis on transparency is designed to prevent exactly this kind of erosion. But transparency only works if everyone plays by the same rules. Here's where it gets uncomfortable. The protocol gives authority to specific bodies: the IAA Committee on SETI, the United Nations Committee on the Peaceful Uses of Outer Space, national space agencies. These are the gatekeepers. They decide when something is credible enough to report, when it's time to consult, when, or if, humanity should respond. But gatekeepers are also bottlenecks, and when the public suspects that information is being controlled, even for good reasons, credibility becomes contested ground. We've seen this play out before. In 1996, NASA announced potential evidence of microbial life in a Martian meteorite. The announcement came from a press conference. It made global headlines. Then the evidence was disputed. Other researchers found non-biological explanations for the features in the rock. The story faded. But the initial announcement had already shaped public perception. The credibility of NASA took a hit, not because they were wrong, but because the announcement was premature. Fast forward to today. Social media accelerates everything. A claim doesn't need peer review to go viral. It just needs a compelling narrative. And when it comes to interstellar objects, the narrative almost writes itself. A mysterious visitor from beyond, strange behaviour, official silence, independent researchers crying cover-up. It's a thriller plot, and people want to believe it. Institutional credibility becomes the only firewall against misinformation. But if that credibility is weakened by perceived secrecy or slow response times, the firewall collapses, so let's game it out. 3I-ATLAS makes its pass. Multiple independent observers detect anomalies, some institutional, some private, some equipped with quantum-accelerated tools that produce results faster than traditional peer review can keep up with. A narrative war begins. One side says probe, the other side says comet. The protocol is supposed to mediate this, but the protocol assumes coordination, consultation, consensus. What if consensus doesn't arrive fast enough? What if the window between detection and public announcement is measured in hours, not months? And here's the question that keeps me up at night. If the protocol's authority is only as strong as the institutions that enforce it, and if public trust in those institutions is already fragile, then what happens when the protocol is triggered for real? When someone has to stand in front of cameras and say, we've made contact, or we've confirmed an artificial object, or we're consulting on a response. Who speaks for humanity? The Nobel laureates, the UN delegates, the live streamers with millions of followers. In the next few weeks, we'll find out. 3I-ATLAS is already visible. Telescopes are tracking it. Data is accumulating. The protocol is waiting in the background, ready to activate if something crosses the threshold from curious to confirmed. The world is watching. The institutions are preparing. The independent researchers are sharpening their tools. And somewhere, in a server farm running quantum algorithms, a pattern recognition system is scanning through terabytes of data, looking for something that doesn't belong. When the stakes are cosmic, credibility isn't optional. It's the battleground.